this direction. We will see later on that it's not exactly like this. In fact, when discussing that, when representing something like this, I have forgotten something, which is this. But I will come back on that later on. Don't mix, let's say, everything. It's already complicated enough like that, but this will not be like that in reality, due to this phenomenon that I have not yet included in my rationale. And this is extremely interesting, because we have found a way to visualize how the engine is reacting in function of the position of the throttle and in function of the flight Mach number, independently of the altitude and the outside air temperature. This is also for A5 that is constant, because I've indicated yesterday that this is true without variable geometry. If I would have a change of A5 for a given Mach number, I would have also different lines if I change the A5 depending on the value of A5 increasing in this direction. Because when A5 is increasing, I'm reducing the speed, so I'm reducing the thrust, so I'm reducing the pressure ratio in the compressor. And this is extremely interesting, because if we have this, which is an easy representation, we can ask us the question, what's happening when I introduce this on this map? What's happening if I introduce this on this map? What's happening if I introduce that on this map? And in fact, what we will do is that we will, on the compressor map, it is somewhere the compressor map that we have indicated here, we will add the different other components. So if we want to consider the compressor map, so first we would need to put the search line, but also we will gradually add the other components on the compressor map, so that we are representing on one drawing the complete engine. So listen, listen, what is our objective? So we would like to represent on just one sheet of paper the complete engine, taking into account the compressor, the combustion chamber, the turbine, the nozzle, everything. This is what we would like to represent. And then we would have the working line or steady state line or different steady state lines that are really the steady state line of the full engine, considering all limitations you have in all components. So the challenge is very large. Of course, you will ask me, why are you doing that? You will see that it will help us to understand a lot of things. Okay? And it is also useful in order to control the engine. You will see that this rationale is extremely important, because the engine control system, the way the manufacturers are controlling the engine, this is coming from this rationale, in fact. This is purely coming from this rationale. The first thing I would like to do, it's a rather easy exercise. This is to think about what is the TSFC reduced and the other reduced parameters. The TSFC reduced, this is what? The TSFC, I remind you what it is. This is m dot f divided by the thrust. Okay? I have already introduced the reduced thrust. This is this. This is what we have called the reduced or corrected, this is the same, roughly speaking, parameter. But what is m dot f reduced? You will say me, the same as here. No, because this is coming m dot, the value we have there, m dot reduced, that is equal to m dot square root temperature divided by total pressure. This is coming from the equation, if you remember well, you need to check, of course, in your notes of compressors. This is coming from the equation m dot is equal to rho VA. But this is not the way we have defined the m dot reduced. The m dot reduced, this is related with the equation m dot f multiplied by QCI multiplied by eta CC, that is equal to m dot multiplied by CP multiplied by TT3 minus TT2. It's not the same equation as this one. So m dot f reduced, it will not be m dot f square root temperature divided by PT. It's not coming from the same definition. And so if you take this equation, you need to reduce all parameters. This is a constant, let's say. This is a constant. This is about equal to a constant eta CC. CP, it's also a kind of constant. And so what will we do? We will reduce m dot temperature TT3 minus temperature TT2. So what can we do? We can divide by TT1 here, TT1 at the entrance of the compressor, so it's TT in my mind. So I need for that to multiply by TT1. So I've done nothing, but it's not m dot TT1 that is the m dot reduced, this is m dot square root TT1. So here m dot f, then I need to divide it by the square root TT1. So you see the TT1 here. And I need also to have PT1 here, PT1 here. This is m dot f. This is m dot f reduced. You see, m dot f reduced is not equal to the m dot reduced. It's not the same. You have the square root in the numerator and here the square root in the denominator. And so the TSFC reduced, this is equal to what? This is equal to m dot f divided by the square root TT1 multiplied by PT1 divided by the thrust divided by PA. This is what you obtain. Now, PT1 and PA is not the same, but you can say, for example, that you divide that by PA, and you multiply then this by PA, so this is dividing this, and you see that you have introduced a reduced parameter. And so you can see that it's m dot f here. You can see that m dot f reduced, this is in fact equal, TSFC reduced, this is in fact equal to the TSFC, because this is here the TSFC, divided by the square root TT1. This is the TSFC reduced. And you see that you are able to define any performance parameter that you would like to use to show it on a map representing this reduced parameter, performance parameter, in function of this and in function of the Mach number, for example, for a given A5. whatever you would like to put here, it can be the reduced thrust, it can be the reduced TSFC, it can be the reduced fuel flow. You are able to do it at the moment that you are able to define what is this reduced parameter. And you see that we have, for example, introduced the reduced thrust, we have, for example, introduced the reduced fuel flow, and we have also introduced the reduced TSFC. And we could imagine other ones, okay? Of course, if you take the fuel to air ratio reduced, you will have this divided by that, and you see that the fuel to air ratio reduced is not the fuel to air ratio. The fuel to air ratio is a reduced parameter, but the fuel to air ratio reduced is not equal to the fuel to air ratio, because you have the TT1 that will be present in this equation. Okay? And so, you have the opportunity to represent here the F reduced. You can represent the TSFC reduced. You can represent the fuel flow reduced. You can represent the fuel to air ratio reduced. You can represent, I don't know, the PI compressor, the PI compressor reduced, etc., etc. Everything you can represent on one map with here a parameter related to the PLA, for example this one, and here another parameter like, for example, the Mach number, for any value of A5. Okay? But I said I'm not satisfied with this. So I have indeed the engine on the compressor map. This is not bad, but I'm not satisfied. I would like more than that. And for example, PT out divided by PT in function of the power lever angle. I don't know what you want to show here. I show it like this because I know that the student was asking, why are you sometimes calling that the PLA, sometimes the reduced thrust, etc., etc. Here it should be, of course, a reduced PLA, but a reduced PLA, it can be the reduced mass flow rate. It's not the reduced PLA, but it's similar, it's the same parameter. Physically, it's the same parameter. Of course, you need to show where are the steady state lines compared to the search line, and then I would like to know where are the steady state line 1, 2, 3 with the Mach number, the flight Mach number decreasing in this direction for A5 that is fixed. I would like to know that. Where are the lines? Are these lines like this, like this, like this? I don't know. And for that, look at what I will do, because a lot of students